Okay, so in this lecture, I'm going to talk about two things. One is going to be the idea of center of mass, but the big thing I'm going to talk to you guys about is the idea of torque. So with the center of mass, basic definition is this is the average location of all of the mass of an object. And so far in our problems, we haven't really thought about this. We just think the idea that, well, the mass is in the center. And that's true. For like uniform objects like this marker, the center of mass, the mass is pretty evenly distributed. So the center of mass would be right here in the middle of this marker. So we don't really think about it. But for like, say this object, like there's a lot more mass on this end. So if I were to think about the average location of the mass, all the molecules here, there's more mass on this end. So the center of mass is going to be more located over here on this side. Okay? There is an equation for the center of mass. We're actually looking at the distribution of mass relative to a particular point. We're not going to go into that nuance of it. So for uniform objects, the center of mass is going to be at the direct center of the object. And another thing, oh, I ran out of space, objects. The other thing to know about the center of mass is if an object is supported under its center of mass, then it will not fall over. It'll be balanced. So for the case of this marker, I don't know if I do this very well, if center of mass is direct center, so if I put a support force right under it, the marker's not going to fall. For this object, ooh, we'll see. My assumption is the center of mass is closer to this side, so if I put, oh, it's rolling. If I put the support underneath there, it won't fall, but if I just did it the direct center, it would definitely rotate. Also, the force of gravity, the weight of an object acts at the center of mass. And so technically whenever you're drawing a force diagram, the weight arrow is supposed to come from the very, very center. And so far that hasn't really played a part, but we're going to start getting into that habit of drawing the weight vector from the exact center. Because of that, sometimes we call it the center of gravity, because that is where the weight is acting. Now, this idea of if an object is supported under its center of mass, it will balance, kind of plays into the idea of what happens when it's not balanced, and that brings us into the topic of a quantity called torque. So torque is the rotational equivalent of a force. So we've been looking at all of our linear quantities and looking at, well, what's the angular equivalent. For forces, it's torque. And so another way to kind of think about this is a torque is when a force causes something to rotate. Our symbol for it is going to be the Greek letter tau. It's like a pie with one leg. The equation for it is that torque is equal to F R sine theta. And torque is actually a cross product. Remember we looked at the idea of what a dot product was when we looked at work, because work was force times distance, but it was a dot product and we got the cosine function out of it. This is going to be a cross product, and we're going to get the sine function out of this. And kind of the difference between the dot product and the cross product is the dot product is going to give you a scalar quantity, but the cross product is going to give you a vector quantity. So torque actually has a direction, whereas work and energy do not have a direction. And the units are Newton meters. Okay. Technically, it has the same units as a joule, but again, because we're looking at the fact that it's a cross product value and it has a direction, we are going to find it as a Newton meter, not necessarily a joule. Let's talk about what these things are. So F is the applied force. R is the distance. Ooh, let's see if I can fit it in here. This is going to be the distance between the force and what's called the pivot point. So this is where the point of I can rotate about, like the axis of rotation. Sometimes it's called the lever arm. Sometimes it's called the radius, because if we think about the fact that it's rotating, the object continue to rotate, it'd be the radius of the circle it can rotate at. And then theta is the angle between F and R. Okay. The video is going to shift, and I'm going to physically model what it looks like to have a torque applied to the door, and kind of give you a real-world example of like, what is this force, what is this R, what is this angle, etc. Okay, so I told you what torque depends on in terms of an equation, but I want to actually model what that looks like in real life. So anytime you have something rotate, you have to exert a torque. And again, a torque is just a force that's applied to an object that has the ability to pivot. So a door is a classic example of something you're going to apply a torque to, because it has this ability to pivot right here at the hinges. So this is the pivot point. So if I were to apply my force here, then my force is here, my pivot is all the way over here. So my R value, my distance, is going to be from where I apply my force all the way over here. So if I want to have a torque to open the door, well, I got to push here, I guess, on the handle. I just have to push with a pretty small force, and it's okay. I'm going to do this block. I don't have to push with much force to get it to open, because there's a certain amount of torque just to open the door. And if I increase my distance, my radius, my force can be pretty small. If I start to decrease my radius, so now I'm going to push here. It's a little harder. I have to push even harder. Decrease my radius even more. So again, my radius is from here to here. I got to push a little harder, okay? If I push here, so like my radius is like 3 centimeters. I can push and push and push really hard. And it takes a lot of force just to open up that door. We've all been in that awkward situation where you go to open the door and you're like, I don't know where the hinge is, and you push at the hinge and nothing happens. That's because if you push at the pivot point, your radius is effectively 0, and it doesn't matter how big your force is. Anything times 0 is going to equal 0, so you have no torque. So hopefully this gives you a visual of what the radius is, force you guys know. The other thing that's a little hard to conceptualize is just the angle. So remember, the angle is the angle between the radius and the force. So if I push like straight on, like straight here, and this is my radius and my force is straight on, this is actually the angle between here and here is 90 degrees. And the sine of 90 is 1. Like that's the maximum, the value of sine you could have is when your angle is 90 degrees. So you'll get the biggest torque possible if you push straight on, so you have this angle of 90 degrees. Now, if we make our angle smaller, what would that look like? That would be like me pushing like this. So now my angle is acute. It's smaller than 90 degrees. That sine value is going to get me less than 1 value, and I'm not going to be as effective. I'm not going to have as big of a torque. You can actually go bigger than 90. So bigger than 90 would be like me pushing this way. Again, this angle is the theta value, and I'm not as effective because the peak value I can get is when that theta value is 90 degrees. So hopefully this gives you more of a visual of what it means for the force, the distance, and the angle when looking at a torque problem. Okay, so because torque causes a direction change, we can't necessarily think of it as going left or right, because at some point the torque may initially be going to the right, but because it's a rotation, eventually that movement right would become a movement left. So it's a rotation, so we're going to define it a little different. So torque is defined as being either clockwise or counterclockwise. So when a torque causes a counterclockwise rotation, it's considered positive. And then the opposite's true. When a torque causes a clockwise rotation, it's considered negative. And that might seem counterintuitive because you're thinking, wait, why, if it's moving clockwise, like that's the way a clock runs, why isn't that considered positive? And our definition actually comes from our mathematical definition of angles. We think about the classic Cartesian coordinate system, and if an object is rotating around like this, like that's the actual direction of like 0 degrees, 90 degrees, 180 degrees, and so counterclockwise is actually the direction of an increasing angle value, so that's considered a positive. And so our definition of direction being positive is going to come out of our math definition of angles. So we looked at the idea of how to calculate what a torque is. We have to take into account the fact that it's got direction. And just like we had problem-solving techniques for forces, we're going to have problem-solving techniques for torques. It's going to be pretty similar to our forces, in that the first thing that's going to drive our problem-solving is definitely going to be a diagram. We're going to draw what's called a torque diagram. And a torque diagram is just like a beefed up force diagram. So it's essentially it's a force diagram that includes the distances from a potential pivot point. So it includes the distance the force is from a potential pivot point. And then you're going to combine your torques. And when you combine your torques, you need to think about the directions. So you have to ask yourself, what direction are they? And just like when you would look at forces and you would say, okay, well, the normal force is going up, the force of gravity is going down, you looked at those forces individually. The same thing is going to apply for torques. Look at the direction of the torques individually. And then combine. And for these first few problems, we're just going to be looking at finding either the net torque that's acting on an object or looking at what is the equilibrium. So in the case of equilibrium, our torques are going to combine to be 0, and everything will be balanced out. So all my torques will be combined to be 0, and all my forces are going to combine to 0. So the video is going to shift, and you're going to look at 2 examples. You're going to look at one of finding the net force in a situation, and then the other is going to be looking at finding the net torque in a situation where you have an equilibrium. And so things are going to balance out, and you'll look at both force diagrams and a torque diagram, but you'll have force equations and a torque equation to help you find enough of your unknowns, okay?